The next speaker is Granger Morgan, who's a professor of engineering, and he's developed a program of engineering and public policy at the Carnegie Mellon Institute, which is really fascinating to me, because normally we don't mix those two areas. Granger has spent a lot of time and careful analyses on trying to understand how to remove carbon dioxide from the atmosphere and the technologies that are available to us and the costs. So the next talk will be Muddling Through on Climate Policy is a good start, but is not enough. Granger?
My title is Muddling Through is Good Climate Policy, but Not Enough. For those of you who don't know Charles Lindblom, to which this is a reference, I'll talk a bit more about that in a minute. So to zeroth order, the climate problem is the energy problem. These are plots from the most recent IPCC Fifth Assessment Working Group 1 showing both the historic rise of consumption of fossil fuels and atmospheric emissions and into the future. So how are we going to decarbonize the world's energy system? Well, international negotiations among international negotiations among 180 nations are all well and good, but what we really need is serious reductions by half a dozen nations or regions. So I've shown here in this pie chart China, which is over a quarter of current global emissions, the US. The EU is sort of spread out here, but it would come next, and then Russia, India, Brazil. And so while having international negotiations is just fine, I don't think the way we're going to ultimately reduce CO2 in a dramatic, to the kinds of levels we need to, is going to result from first 180 some odd nations all agreeing and then we all get on board and proceed. I think it's far more likely that the strategy that succeeds will be that individual parts of the world, the US, China, the EU, each develop a strategy and then gradually over time these get coalesced. So that was the argument that I actually made 15 years ago in a policy forum piece in Science, which said it's fine to have these international negotiations, but we ought to be devoting some attention as well to the issue of how over time might you coalesce these different regional arrangements. So in that light, because it covers close to half the world's CO2 emissions, the recent bilateral agreement with China is a very important step forward. It may involve incremental muddling, but for the first time it gets the two nations that produce the most CO2 talking to each other about specific steps to reduce emissions. Chinese emissions are committed to peak in 2030 and then not grow after that, so it's going to get China off the exponential growth that has characterized things there up until now. And EDF actually reports that at present China has carbon trading programs in 5 cities, 2 provinces that cover over 2,000 sources. 16% of total greenhouse gas emissions are covered by these. Now, here in the United States, if the Waxman-Markey bill had passed, it wouldn't have been perfect, but it would clearly have been a much better strategy than using Section 111 of the Clean Air Act. But we've got Section 111, and it's better to get started with something than to continue doing nothing. Which brings me back to the title. Charles Lindblom, a political scientist back in 1959, wrote this paper, which has become a classic in the policy field, called The Science of Muddling Through. And it argues that sometimes it's a whole lot more effective to take existing strategies or policies and incrementally modify them than to try to come up with efficient, comprehensive designs and put the whole thing in place at once. And so that's the source of the title. However, if climate policy is ultimately to be successful, muddling will need to be combined with some longer-term visioning. Modest first steps that reduce emissions of greenhouse gases are wonderful, but to stabilize the climate, the world must reduce emissions of greenhouse gases by at least an order of magnitude So it's not too soon to start thinking about how to avoid getting stuck with policies that don't scale up, how to avoid regulatory lock-in, and to move past early incremental steps to achieve deep reductions. Now, the U.S. is finally getting serious. Under Section 111B, we now have limits on new sources that are set at roughly the emission rate of a gas-fired power plant, and which means that if you're going to build new coal plants, you're basically going to have to do capture and sequestration. You'll hear more about that later among the talks. Under Section 111D, which applies to existing facilities, EPA has proposed a variety of strategies to try to reduce emissions, and their objective is a 30% reduction by 2030. However, this is going to involve specific different strategies in different states or regions. It's going to be a very complicated mix of approaches, and to assist in this process, my colleagues Paul Fischbeck, Haibo Tsai, and Jeff Anderson have developed a model that characterizes every coal-fired boiler in the United States. I'm not going to walk you through the details of this model. The central element there that says IECM is the Integrated Environmental Control model system. It's a whole family of models that Ed Rubin on my faculty has developed over the past 30 years or so. These are large stochastic simulation models of conventional, advanced coal combustion systems that produce estimates of cost and output and so on, all as full probability distributions using the very best available data, including data on things like amine scrubbing, a new module on oxyfuel, and so on. And then this model has very comprehensive user interfaces that allow you to go in and look historically at how things have performed, to do forecasts, to look at state-level details, and then to do boiler-by-boiler specific assessments. If any of you, incidentally, are working in this space, I believe that these guys are on the verge of releasing this stuff publicly, and so let me or them know, and I'm sure it's a model we could share. However, there's a risk that the plethora of very different state and regional strategies that result in some limited reductions, 30% if we're lucky, of CO2 emissions may not readily scale up to larger future reductions. And while I'm not going to talk about it today, there are similar sorts of risks at the international level. For example, the ICAO has a proposal out for dealing with airlines that's incredibly complicated. Fortunately, I don't think it's going to get accepted, but it nevertheless, if it were accepted, would make life much harder to get past these initial steps. And so the basic argument is we need to figure out, first of all, how we might get ourselves into dead ends and then how to avoid them. Now, hopefully litigation isn't going to derail the present Section 111 strategies under the Clean Air Act, and the U.S. will achieve 30% reduction, but 30% is less than a third of what we actually need to achieve, and moving beyond the resulting complex patchwork of state-by-state regulatory solutions will pose some big challenges. So we should applaud incremental progress on emissions reductions in the face of implacable political opposition, but there's no escaping the need for an order of magnitude reduction in global emissions of greenhouse gases. Changing complex regulatory systems, once they become firmly established, can get extremely difficult. Hence, I believe that for each piece of incremental progress, the policy research community needs to start now to ask how best to avoid technical or policy lock-in or dead ends, and to identify strategies that will readily allow us scale up to large future reductions. The resulting challenges in regulatory and policy designs will be daunting. However, without those designs, progress could stall, and success today shouldn't become the burden of tomorrow. Everything I've said up to now, I said in 600 words for a draft editorial that I shipped to Science. And Science came back, Marcia McNutt came back to me and said, Granger, you've made a very compelling case, but you haven't said how to solve the problem. In 600 words, that's a little hard to do, so I'm now in the early stages of trying to turn this into a policy forum where you get a few more words, and that's what I want to talk about now for the balance of this talk. Here's the U.S. energy system, and I'm going to talk about it by sort of walking us around the U.S. energy system. Most of you have probably seen these plots that Lawrence Livermore updates on a regular basis. On the left-hand side there are sources of energy. In the middle are our various conversion technologies. The pink boxes on the right are the various end uses. And then here, the light gray is rejected waste heat, and the black gray is useful output. So let's start, let's start by looking at ways to promote low or zero CO2 energy. And I'm going to talk about 4 examples, beginning with one involving capture. DOE should mount a program to coordinate with states and or other utilities and IPPs, independent power producers, that want to meet part of the Clean Air Act Section 111 obligations with carbon capture and sequestration by providing subsidies for commercial scale CCS. We really haven't built any large commercial scale CCS plants. There's a few in the works at this stage, but it's been much slower than it should have been. Such a program should pay special attention to strategies such as oxy-fuel that can reach 100% capture. So here are cumulative distributions on the cost of CO2 avoided in dollars per ton of CO2. For the blue line is oxy-fuel, and the red line is a mean capture, and you know, there may not be, and this is a very modern, detailed analysis, but it's not clear that you should put a lot of faith in that difference. What you should, however, note is that when you look at what can be achieved, oxy-fuel can get you to 0, and a mean can get you sort of 90% without too much difficulty. What?
A lot of the audience doesn't know what oxy-fuel is.
Oh, sorry. So I'm being told that some of you don't know what I'm talking about. So there's 3 ways to prevent CO2 from a coal-fired power plant getting into the atmosphere. One way is run the normal plant, put a scrubber on the back end. That's what I'm talking about, a mean capture. That captures the CO2 and then puts it a kilometer or so underground. A second way is to take the coal right up front and gasify it, and then use the resulting hydrogen to produce electricity. And the third way is to make pure oxygen and figure out how to modify the combustion process so you don't have temperatures that are too high. Burn the coal in pure oxygen, and then, unlike the conventional plant where you get rather dilute carbon dioxide out the back end, you get a very concentrated carbon dioxide out the back end, which you can then capture and sequester. And I think the last talk of the day will elaborate on all of these ideas. So here's a second example. We're still on the emissions, on the generation side. Congress should adapt a regulatory framework that's similar to one that we developed in a draft, as draft legislation in a project we ran for several years called the CCS REG project. CCS stands for carbon capture and sequestration. REG, of course, refers to regulation. If your library doesn't have a copy of this book that we produced through RFF Press, let me know and we'll ship you one. At the moment, the regulatory situation is different in different U.S. states. In some states, the issues of who owns the deep pore space is a real mess in this country. And furthermore, the current EPA rules don't address issues like who owns pore space, what liability regimes apply, what are long-term stewardship arrangements. We worked through all of these issues in this book, and then because we had several first-rate lawyers as part of the project, we produced a 50-page draft bill in the back of the book as an appendix. We don't expect, we're not naive. We don't expect anybody to actually pick up this bill and pass it, but we also know how bills get written. which is they cut and paste. And so here's a ready place to start cutting and pasting if and when folks get serious. Here's a third option. States, regions, and the federal government should develop strategies to sustain the present fleet of nuclear plants in the face of low-cost natural gas and other competitive pressures. We've restructured the electricity system so that now short-term economic issues pretty much drive the system, and so we have a number of nuclear plants across the country that have either been shut down because they're not competitive with natural gas or are in the process of being shut down. Several plants have closed, as I said. My understanding is that the closure of the Kewanee plant was entirely economic, that Vermont Yankee and San Onofre needed some work, but you know, when owners looked at the situation going forward with really cheap gas, decided it wasn't worth making those investments. And recently, a senior executive at PJM told one of my PJM is the region of the electricity region that we're sitting in, actually. Recently, a senior executive told one of my colleagues that he thinks 5 or more nuclear plants are at risk as a result of low natural gas prices. This is the result, as I said, of short-term economic focus imposed by restructuring, but it's nuts, given that soon the nation is going to have to get serious about decarbonizing our energy system. And to do that, we're going to need absolutely everything we've got, and we're shutting down large carbon-free generation plants. And the final example I want to mention is small modular reactors. These are reactors of smaller than 300 megawatts, a few hundred megawatts, that could be potentially manufactured in a factory and then shipped intact to sites. The advantage is that you could get costs down and you could probably get reliability way up. We actually ran a workshop a couple of years ago at the Paul Scher Institute in Switzerland, which is the Swiss Federal Nuclear Lab, in which we had 3 reactor designers from China, 2 from Russia, 1 from Korea, all the reactor designers, manufacturers from around the world. What I can tell you is that there are going to be SMRs and they are going to get exported, but probably the US is not going to be a player because things are pretty much stalled out. While the DOE does have a program, it's not looking terribly hopeful at this stage. Let's talk about the other end of the energy system. It would be awfully nice if we could move more of that light gray down to the dark gray. That is to use the energy we consume more efficiently, and I'm going to give you 3 examples in this case. The first is to use more distributed generation with combined heat and power. At the moment, we make most of our electricity out at large generating stations, and you've seen the cooling towers with the plumes of steam coming off the top. That's rejected heat. That's why there's that big light gray region. If instead I use it locally and capture that heat and use it for heating or cooling, then I can almost double the efficiency with which the natural gas I put in the front end gets turned into useful things. Now, there are some problems, and in parallel, DOE needs to work on doing a couple of things. First of all, suppose we were dramatically successful in achieving this. Then we would have committed to using natural gas in lots of distributed small sources. Now, it's possible to capture and sequester CO2 from large gas plants, but it isn't going to be possible to do that from many distributed sources. So one needs to figure out some way over time to not be using methane, or at least not be using methane that's from geologic sources. And we need to find ways around state laws that grant distribution utilities exclusive service territories so as to promote the growth of small microgrids. These systems work better. There are economies of scale. So you'd like to use them at slightly larger scale in individual houses. You'd like, for example, to power a shopping center or a small industrial park with these things. But at the moment, the big impediment to innovation in this space is that only conventional legacy utilities can sell electricity to anybody else. So there's an opportunity to change state law to implement distributed generation with microgrids down under the existing distribution system. In the efficiency space, empirical assessment is really essential. And I'm going to give you 2 examples on this slide. This paper is something that was published in the Proceedings of the National Academy a couple of years ago by a group in my department. For those of you who don't get the reference, the Hawthorne effect is a result observed in studies done in the manufacturing labs of the old Western Electric plant in Hawthorne, where they discovered that workers behaved differently if they were being observed than if they weren't being observed. So in this study, the investigators had access to very large numbers of smart meters. And they went through all those customers and they matched 2 customers to be more or less identical. And then half the customers got postcards that said, "You're in a study on electricity use." And the other control group got nothing. The impact of doing that was about the same magnitude as the impact in terms of reduced electricity consumption that O-Power gets routinely by charging utilities thousands of dollars to run promotional programs for energy efficiency. So the first message here is you really got to worry about what the causal relationships are. It may just be that raising people's concern and focus on energy efficiency is all that's needed. This second study is something that my colleague Inés Azevedo and one of her doctoral students have just done. This is in California, a utility program to promote the adoption of more efficient appliances. And the blue plots on the top show you the number of participants. On the bottom here, it looks at the change in energy consumption after participation. Ignore all the stuff to the right. That's to simply look at people who participated in multiple programs. The first couple of plots where you can see a 5 or 6% increase in energy consumption are the results from just this program. So why are you doing this? Why are you seeing this? You're promoting more efficient appliances and energy use actually goes up? Well, because in designing this program, they didn't require that you turn in the old appliance. So, you know, people are still running their inefficient refrigerator in the garage or doing other such things, and net energy consumption went up. So the key point is you really got to do empirical assessment. Here's a third example of the same sort. There have been lots and lots of studies of energy efficiency that have been run by utilities, and Baruch Fishoff in my department has created a small group of wonderful young behavioral social scientists who have, among other things, gone and systematically looked at all of those studies done by utilities. I won't go through the details because time is short, but the bottom line is that design problems are horrendous. People have not been designing these studies very adequately. The new ones that are just now getting started are getting much better, but one really needs to be careful to use good modern experimental social science methods if you're going to try to understand whether these things are working. The last focus is on the whole system and on greenhouse gases and on adopting strategies that scale. And I'm going to give you 2 examples here. State legislatures should substitute carbon portfolio standards for renewable portfolio standards. And analysis groups ought to lay the groundwork to support easy adoption. If that's what we care about, if CO2 is what we care about, why not focus on it directly? And furthermore, you know, while wind and solar and hydro have strengths, they also have some large environmental impacts, particularly land use. For example, this is a second book that I'd be happy to ship a copy to if your library hasn't got it. This was a project similar to the CCS REG project that was led by Jay Apt, where we looked at the problems of integrating variable and intermittent renewables into U.S. power systems. And the answer is you can get up to 30% without much electrical difficulty, that is, without problems of dealing with the intermittency. Jay's strong assessment is that getting much beyond that is going to run into strong opposition more on land use issues. People just don't want a lot of this stuff around. In the Netherlands, for example, which we think of as, you know, windmill country, there's now enormous pressure to get this stuff offshore so you don't have to look at it. And there are significant environmental impacts from wind. Here, for example, are pictures of habitat disruption from wind farms along the ridges in western Pennsylvania. And there are, of course, also bat and bird and other issues that really require serious consideration. His position is a little extreme, but Jesse Ausubel has argued fairly forcefully that renewables aren't green because they use so much land and other resources. Second example I want to use is that analysis groups should help states develop ways to avoid or minimize the use of point source control strategies that aren't easily superseded by pricing emissions or by cap and trade, which is, of course, the way we ought to have been doing it in the first place, but is not the way we're going to end up doing it for much of the activity under Section 111D. So the real efficient way to control CO2 emissions from things like power plants is to simply impose a fee or impose a cap and have trading. On the other hand, while emission taxes or cap and trade are sensible for point sources like large power plants, performance standards such as CAFE, in my view, make much more sense for sources like motor vehicles. $1 a ton on CO2 emissions translates to about a penny a gallon at the pump. I cannot imagine the political strategy which in the next decade or two gets us carbon prices much above $20 or $30, and I can't imagine a 20 or 30 cent change in the price of gasoline fundamentally transforming the vehicle fleet. So I'm a strong proponent of performance standards for those sorts of applications, but emissions taxes or cap and trade for large point sources. So my bottom line is that muddling through may be the best we can do in the short term in order to get started on policy to reduce CO2 emissions. However, to avoid dead ends, to not get stuck with regulatory capture or regulatory arrangements that are impossible or very, very difficult to change, the community of policy analysts need to begin to work now on identifying and avoiding strategies that might lead to those sorts of dead ends and find ways to promote strategies that will in fact scale up to the 90% or more emission reductions that we need. And with that, I say thanks.
Granger, thanks very much. I've been involved heavily, as you know, in carbon capture and storage for a very long time and have had an epiphany. I do not believe there is a chance in the world of that ever succeeding. Therefore, I think that from a systems point of view, one should be looking at other distribution strategies. I fully agree with your CHP modeling and with the change in regulatory issues with regard to distribution, sale of electricity. Those monopolies which are fostered by business enterprises operating through government edicts should be changed. So that I would suggest an alternate complete system model in order to generate the amount of energy that we need and can consume efficiently.
The previous version of this talk had a title, something to the effect of reducing carbon dioxide emissions from the energy system is going to take everything we've got. And if indeed you're going to achieve a order of magnitude reduction at an affordable cost, I think that carbon capture and sequestration has to be part of the mix. I just cannot see how you do it without that. You are absolutely right, however. The pace at which we have built these things have been very, very slow. And on the other hand, if the price of emitting a ton of carbon dioxide to the atmosphere were $80 or $100, I think you would find that people would suddenly get interested. But it isn't. I mean, at the moment, it's free to emit carbon dioxide to the atmosphere. And so the fact that nobody's built, we've done a variety of small-scale demonstrations. There are a few hundred megawatt plants being built around the world. But the fact that we haven't got very many is, I think, largely the consequence of just not having a serious constraint on emissions of CO2. I mean, you and I can discuss privately whether or not, what fraction might happen. But I don't see how to get there without essentially a portfolio of absolutely everything we've got. And even then, we're not going to hit a 2-degree target. I mean, I had a chat with a senior environmental reporter a couple of months ago in which he asked me about, what were my views of hitting 2 degrees. And I said, well, it's nice to have objectives like that, but they got to be objectives that you can actually realize. I'd like to be 40 next year, but it ain't going to happen. We got one other?
Yeah, so Steve Member.
Yeah.
Yeah, so quick, on the nuclear, I think you left one piece out that I think I would encourage you to talk about, which is the fact that we have licensing. So most of the plants are now in a relicense phase. The IEA is assuming another relicensing, but most of the economists and most of the plant operators don't see that as feasible. In 15 years, we hit what I refer to as the nuclear cliff because of the relicensing. So a lot of the decisions that you talked about are based on trying to sort that out. And I think that it's not just about the competition with natural gas, it has to do with about the feasibility of long-term investments.
Yeah, it's a factor, Steve, you're right. On the other hand, we're not building nukes in this plant. We're building 4 nukes in this plant, and there's a restart on a TVA 5th plant. The 2 nukes are the 2 sites where we're building those 4 nukes are all in the southeast, where there are vertically integrated utilities still that can take a somewhat longer-term perspective and persuade their PUCs that this is a prudent investment. But in a system where short-term market considerations predominate, there's no way that nuclear power is going to play a role until either the price on carbon gets very high or we have some longer-term planning horizon. I mean, one of the reasons we've done a big piece of work on small modular reactors because at least in parts of the developing world, they may be a way to help with decarbonizing local energy systems, but this is work that has been funded by the MacArthur Foundation to worry about proliferation risks. We think actually that those can be managed, and be happy to share writings on this subject with anybody who's interested. The one problem at the moment is that SMRs are just still priced, they're just way too expensive. One last thing, I mean, when I say I think to get a serious control of CO2 is going to take literally everything we've got, and even then we're going to have great difficulty doing it. If you take nuclear off the table, if you take CCS off the table, it just gets horrendously expensive. Yeah.
Granger, I thought that was a wonderful talk. I wondered why you chose not to talk about energy storage. Is it a genuinely lower priority for you?
No, quite the contrary.
Or do you just have 30 minutes?
You do need storage. Where you put it is a bit of an open question. Whether you ought to put it, out near wind farms that are intermittent, or near near coal plants that are hard to ramp up and down quickly. But I actually think that energy storage is very important. And my colleague Jay Whitaker, who I hired years ago from the Jet Propulsion Lab, has started a company called Aquion that is very successful in this space. It's a carbon-based design with an aqueous electrolyte that is very benign. You could essentially drink it. So Jay helped design the batteries for the Mars rover, and when he joined our faculty, he said, now cost is an object. And so this design came out of that. And so I think it's really very, very important. It's just that there's a limit in a few slides as to how much you can include. All right, well, thank you very much.